All right, so we're looking at part 2 of Leibniz notation for derivatives and average and instantaneous rates of change. This happened to be a slide from my first video, and I just wanted to put it up there for an introduction. And I wanted to make one additional comment about some of my terminology. So I said the delta notation, that's the average rate of change of, say, that variable on top u with respect to this variable on the bottom t. Okay, and the derivative du over dt is the instantaneous rate of change of the variable on top u with respect to the variable on the bottom t. Okay, now in practice, usually the word instantaneous is left out. So when somebody says rate of change, they mean instantaneous rate of change. They mean the derivative. And if we intentionally want the average, then we mention average. All right, but so I told you in the first video, I told you the difference between these. But in the future, or say on assignments, or when you hear other people talk about this, they'll probably just say rate of change of u with respect to t instead of instantaneous. The word instantaneous is implied, in other words. All right. So let's do an example to continue what we started in that first video. Here we go. So here's my situation for you. Suppose that a painter needs to paint 750 square feet of wall space, okay? And the painter can work at X square feet per hour. So that number is not specified, but there's got to be an average rate that a painter works, right? If you measured how many square feet you could paint and how long it took you and you divided them, that would be your average work rate, okay? So the painter works at so many square feet per hour. The painter can paint at so many square feet per hour. And the painter gets paid $50 per hour. Now, let's suppose from there that P is the total payment for painting this 750 square feet, okay? All right. Can you find P, the total payment for this job, as a function of X, the average work rate, okay? Can you find P, the total payment for the job, if the painter paints at, what was X again? 100 square feet per hour, all right? And can you find the derivative dp over dx, or the derivative of P with respect to X, when X is equal to 100. All right, so those are the three things that I'd like you to be able to find with this. So let's start with, in order to find the derivative, it has to be the case that that variable on top, P, is a function of this variable on the bottom, X. So that's why we need to find P as a function of X before we can do this, all right? So let's start by finding P, the total payment for the job, as a function of X, the average work rate in square feet per hour. All right, so here's my explanation on that. So you would find P, the total payment for the job, as your payment in dollars per hour times the number of hours that you worked. That's how it would be, right? Okay, now I know that it said up there that we're getting paid $50 per hour. How many hours it would take, that wasn't given, all right? But I can find that from the average work rate and the amount of wall space that I'm painting. All right, so sure. Take it like this. So if I take 750 square feet, that's how much wall space I'm painting, and I divide by X square feet per hour. That's being the speed that I paint at. Look at how the units work out. I got the number 750 divided by X. I've got square feet on top divided by square feet per hour on the bottom. You can analyze units like this. What are the units of this number? If you take 750 and divide by X, what are the units of what you get? Well, the square feet cancel out of it, and the units will be hours. So that's $50 per hour, and that's the number of hours that you'll be working. Okay. So if you multiply 50 times 750, then you'll get 37,500. So here we go. P, the total payment of the job as a function of X, the speed at which you work is going to be 37,500 divided by X. All right? Okay, so there's my answer for the first part. Now, what is P if F is 100? Or what is P if X is 100? Meaning, suppose that you can paint at 100 square feet per hour. How much are you going to get paid to paint the 750 square feet? Well, if you put 100 into this, that'll be 375. And does that number have units there? What are the units of that number? P is a function of X. P is the total payment for the job. X is how fast you paint at in square feet per hour. Well, the units of P are in dollars. Okay. So I get 1, my function. P is a function of X. If the work rate is 100, I'll get paid $375. All right. Now, what's dP over dx? That's the derivative of this right here. There is a function where P is a function of X. You're looking at that right here. dP over dx is just the derivative of that function, okay? But it means that if X were to change, how would P change? So I'll make a prediction about this. What do you think if, remember in our other video, the first video I made, where I said, if you have any function, all right, like this one, and you calculate the changes of the variables, like one variable changes and another variable changes, and you find the rate of change between them, then the derivative of that function is roughly going to be equal to those actual changes, okay? The derivative is just a formula and a rule. The deltas are the actual changes, but they'll be very close. So that's how you can interpret the derivative. You can say, if these variables were to actually start changing together, that's the rate of change I would get, okay? All right, so here's what I'm thinking. I'm going to predict something about this. I'll predict that it will be a negative number, okay? And here's why I'll predict it's going to be a negative number. Because as one of these goes up, the other's going to have to go down. Suppose you're painting 750 square feet. All right, okay, and you get paid $50 per hour. Isn't the faster you work X going to mean the less your total payment for the job is? I mean, suppose it took you, I don't know, I mean, suppose you could paint 1 square foot per hour. That's not very fast. It's going to take you a long time to do that. And you get paid $50 an hour, you're going to earn a lot more money. But suppose you paint 750 square feet per hour. Well, you could paint this whole space in 1 hour and get paid $50. So yes, the faster you work, the less time it's going to take you and the less your total payment is going to be. So if X is going to go up, P is going to go down. That's just the nature of this function. It's just the nature of the situation. If X goes up, P goes down. The faster you work, the less that you're going to get paid, all right, to finish this job. Now, so let's do this. To find the derivative dP over dx, I'm going to write this function a little bit different. When I had in other videos taught you how to calculate derivatives, then I usually wrote the functions in very specific ways so that the rules would apply to them. So instead of having 37,500 over x, I'll say 37,500 times x to the minus 1 power. And then if I look at that, I'll find that dP over dx is 37,500. All right, we're going to carry that constant factor right there, that coefficient over. And then we're going to get negative 1 times x to the negative 2 power. So your derivative is going to be negative 37,500, okay, over x squared. There's your derivative. So I had predicted that's going to be a negative number. If these two variables both increase together, the derivative will be positive. If these two variables both decrease together, meaning when one goes down, the other goes down, the derivative will be positive. But if one of these goes up, causes the other to go down, or vice versa, the derivative will be negative. It is negative, all right? You get negative 37,500 over x squared. That'll be a negative number. So let's put 100 in and see what we get. when you put 100 into this derivative, that's what that means, okay? That right there says find the derivative and put 100 in for the variable x. Then we'll get 375. It'll be 37,500 over x squared. And it'll be negative. 37,000 over 500. 37,500 over 100 squared. All right, so that's what you'll get. Does this number have units? Okay, well, the units of this number, the units of the derivative, will always be the units of the variable on the top over the units of the variable on the bottom. So here are my units. Okay, what are the units of the variable P? That's our total payment for this job. So that will be dollars. Okay, and what are the units of the variable X? Well, X was how fast we can paint, how fast we can work. That's going to be square feet per hour. Okay, all right. So negative $3.75 per square foot per hour. So here's how you can interpret that number. One, I give you my number. Two, I'll interpret it for you. Remember in that other video, I said that the derivative and the deltas are going to be fairly close to each other. This is telling me how, as I get faster, my total payment for the job is going to change. Okay? So it's like, you know, this is going to be roughly equal to delta P over delta X. All right? So that's going to be roughly equal to negative 3.75 over 1. So it's like saying this. For every square foot per hour faster you work, you get paid $3.75 less for this job. Okay? So remember, that's how we can interpret that number. The derivative is roughly equal to the deltas, the actual changes. So delta x is 1. Put a 1 under there since it's not a fraction. Delta p will be negative 375. Yes, so for every square foot per hour faster you can work, you'll get paid $3.75 less because of the negative. All right. So that's my first example I want to show you. Let's look at I think 3 more, 2 that are fairly easy, and then 1 that's more involved. So let's do this. There's something that comes up in the assignment that I wanted to talk about, and it's what it means for something to be proportional, or for one thing to be proportional to another thing. And I thought I could mention this and kind of jump off the last example I was doing. So can you write an equation for this scenario? My payment is proportional to the number of hours I work. Well, that's like for anybody that works at an hourly rate, that's a familiar situation, okay? So here's what it means for one thing, payment, to be proportional to another thing, the number of hours you work. P, the payment, is equal to K times T. T is the number of hours you work. P is your payment. K is called the constant of proportionality. And in this particular case, it would have units in dollars per hour. All right? But, you know, for anything, payment to be proportional to some other thing, number of hours worked, it just means we're multiplying by some constant K. That constant may or may not be known. All right? But that's how it fits in. Now, here's one problem that is similar to that one, but it deals with a law of nature called Newton's law of cooling. And I think everybody has seen this happening, where the temperature that something changes at depends on how different it is from the surrounding temperature. So like if you put a room temperature glass in a sink full of water, nothing really happens, okay? Because let's say the temperatures are roughly the same between the glass and the water. But if you take like a extremely hot glass right out of the oven, and then you throw it into a sink of water, then it shatters, it cracks, and that's because the temperature that the glass changes is very fast, okay? It's changing temperature very fast. That's what causes it to shatter. And that's why it doesn't shatter if you put it in and it's roughly the same temperature of the water, okay? Now here, see if you can see why I think that's an analogy to this. It says the instantaneous rate of change, or the rate of change of t, the temperature of an object, with respect to little t time, is proportional to t minus t sub a, where t sub a is the temperature of the surrounding medium. So that just means that an object will change temperature faster the more different it is from the surrounding temperature. Okay? But to put it in terms of an equation like that, we'll do like this. See this word proportional? Okay, I used it exactly like in that example. So it says the instantaneous rate of change of t temperature with respect to little t time. So our symbol for that is dt over d little t. Okay? Is proportional, that means there's going to be some number k that I multiply by this other thing proportional to the difference of the temperature of the object and the surrounding temperature. So T minus TA. Okay. So that's this law of nature expressed as an equation. This is how fast the temperature is changing. Okay. And why do I think that's how fast the temperature is changing? Isn't the derivative roughly understood as the actual changes of those variables? Isn't that true? Isn't that something I've been emphasizing in our lesson? So how do you measure a change in temperature? It might be like degrees Fahrenheit. And how do you measure a change in time? Well, that could be in minutes or seconds or hours. But, let's say I'll use hours. So there, it's like this is telling me how fast something is going to heat up or cool down is depending on how different the temperature of it is from the surrounding temperature. See this minus? That subtraction is going to be bigger the more different those things are. Okay, so there I expressed that law of nature as an equation. It involved our Leibniz notation for derivatives, and you got to know what it means to be proportional. Okay, let's look at another one. One last example for this one. I'll save the hardest one for the last problem, but here's our situation this time. It says the radius of a right circular cylinder is root t plus 3 inches. So first of all, what does that mean? I guess it means that if I tell you t is time in seconds, that this shape is morphing, it's changing. The radius right there is changing from moment to moment. And that happens with, like say you have a metal object and you heat it up or cool it down, it might very slightly change size. Okay? But all right, so we're going to accept this at face value. The radius of, which is that, distance right there, is root t plus 3 inches. You tell me the time, I can tell you the radius. If t is equal to 1, then the radius there is 2 inches. All right. The height is 1/3 root t inches. Okay, so that's the height. So it's getting bigger too at time. All right, so you can say, well, if t is 4, if that's the moment you're talking about, then the height is 2/3 inches. All right. Can you calculate the following? Can you give me the volume as a function of time? Can you find delta v over delta t? If t is 4 and delta t is 0.01. Can you find the derivative, dv over dt? And can you find dv over dt when t is 4? Okay, so I want to find 4 things here. So here in my picture, that's what a right circular cylinder is. And there's your volume for it. It's pi times the radius squared times the height. All right, so let's see if we can work this out. So here, both the radius and the height are functions of time. You have to know the time to figure out the radius and the height. That's what it means when they were given that way. So let's do this. We'll say the volume is in general pi r squared h for this shape. Pi is a constant. It's about 3.14. Here you're telling me the radius is root t plus 3. So I need to square that. And then the height is 1/3 root t. All right, so that must do it, right? That's got to be it, because that's how I told you you would find the volume of such a shape. So let's do a little simplifying. So I get pi. If I square the root of t plus 3, then I'll get t plus 3. They'll cancel. All right, it's sort of like, what's the square root of 4 squared? I guarantee you it's 4. Let's see. What's the square root of 4? That's 2. And what's 2 squared? Oh, that's 4. So yes, they'll cancel each other. And then this is 1/3 root t. So here's what I would like to do. I'm going to put my constants together. I mean, this is all multiplied, so I can multiply this in whatever order I want. So I'm going to see this as pi times this times 1/3 times root t. Let's write pi over 3. Okay, and then let's distribute since this can be combined, the root t in there. So what's t times root t? Well, when we multiply like things, we add their exponents. So that's going to be t to the 3/2 power. Because the power there is a half. And what's 3 times root t? That will be 3 times t to the 1/2 power. And I'll go ahead and write it with the 1/2 power instead of the root. All right, so there is v as a function of t. Let me give you my answer over here. Okay, pi over 3, t to the 3/2 power plus 3t to the 1/2 power. All right. Volume is a function of time. So you tell me the time, say the clock's ticking and the radius and the height are getting bigger. You tell me the moment in time, and I can tell you what the volume is at that moment. Remember, when we have our functions, one of the variables is intended as an input, and the other is an output is calculated from the input. All right? Okay. Now that we have this function, we can calculate our delta, our changes. So I might wonder, well, how does the volume change in time? Like, I know it's getting bigger, but it's getting bigger by, like, let's see. So you're measuring everything in inches here. Like, maybe like so many cubic inches per second or something like that. I mean, this shape's getting bigger. If I calculate these deltas, that'll be roughly how fast it's getting bigger. All right? So let's see if we can do that now. How have I done this in the past? Here's how I, like at least in that first video, here's how I did it. All right. So let's say you got t and you got v. And delta v over delta t is just a measurement of how they're changing together. All right. So we want this to be 4 and 4.01. And v, how are you going to find v when you have t? Well, from the function. You put t in and you get v back out. So that's going to be pi over 3 t to the 3/2 power plus 3t to the 1/2 power. All right, now, say you do the math on this. Say you put 4 in, probably with the help of your calculator, and 4.01 in. Then here's what you'll get. You'll get about 14.661 for this one, and if you put 4.01 in there, you'll get about 14.700. Okay, so all right, those are the numbers we need. If you calculate delta v over delta t, then that's going to be this number minus that number. That's the change in the volume. As time went on, the volume got just a tiny bit bigger, right? It went from 14.6 cubic inches to 14.7 cubic inches. All right, it did get bigger, but the change in V is 14.700 minus 14.661. And then the change in T, well, from 4.01 to 4, that's going to be 0.01. All right, so let's see what that turns out to be. 14.700 minus 14.661 divide by, so you'll get about 3.9, roughly 3.9. And that's with some rounding, but that's about what you'll get, okay? All right. Now, so let's so my answer for this, 3.9. Now, this has units, though. And we'll start paying attention to units when we do problems that deal with measurements and laws of nature and so on. And it can be done in a science class. then we'll always keep track of our units. The units in this number, well, think about it. How do you measure volume? My radius and my height were given in inches. So this number up there, delta V and V, is going to be in cubic inches. That's how you measure volume if your length measurements were in inches originally. So that's like 14.661 cubic inches. It got a little bit bigger, 14.7 cubic inches. The volume changed by that subtraction right there in cubic inches. And what about this? T, time. It says we're measuring time in seconds, all right? So that's going to be seconds. So when you calculate delta V over delta T, you're telling me the change in volume in cubic inches over the change in time in seconds. All right, so this number will be cubic inches per second. Let's pay attention to the units. If you ever took a science class, like a chemistry or physics class, you get in trouble if you don't pay attention to your units, okay? All right, so next part. Can you find the derivative, dv over dt? So that's a derivative, but it's a derivative of what? On paper somewhere, is that variable v a function of this variable t? So yes, that's where I started. This is the derivative of that function. All right, so let's start there and we'll figure it out. So I'm going to say v is pi over 3 t to the 3 over 2 power plus 3t to the half power. Okay, the derivative of this, dv over dt, v being the output variable, t is the input variable, v is the dependent variable, t is the independent variable, is going to work like this. I got a constant times a function. I'll carry that constant down in this case. Here I'll get 3 over 2 t to the 1 over 2 plus, I carry this 3 down, bring the 1/2 down, I'll get 3 over 2 again, t to the minus 1 over 2. So there's your derivative, but how about this? I can factor out the 3 over 2. It's common to both terms. If I factor that out, that's going to look like pi over 3 times 3 over 2. The 3's are going to cancel. And I'll get pi over 2 times t to the 1/2 plus t to the minus 1/2. Okay, so there's my answer for the derivative. Let's write that over here. So dv dt, pi over 2 t to the 1/2 plus t to the minus 1/2. Now the derivative will have units just like the deltas. The derivative is supposed to be roughly equal to the deltas. Okay? It has units of volume over time. The derivative always has units of this variable's units, volume on top, over that one's units, time on the bottom. So when you calculate this number, its units will be in, well, volume in this case is cubic inches per second. Time is in seconds. So it's going to be just like delta V over delta T. All right, so I got my derivative. What is the derivative when t is 4? Okay, well, given that we have the derivative, that should be easy to do. We just got to do this and this, okay, and do the math. I'll do a little rounding when I do that. So let's see. So that's 2, that's 1 over 2. And then times pi divided by 2. So I get 3.927. So it's about 3.927. All right. 3.927 what? Does it have units? Yes, it has units. Volume over time. In fact, it's just like delta V over delta T. I explained the units for that, all right? I told you, where does inches to the 3rd power and seconds come from? I explained it. So this is also inches to the third power over seconds. It has units, like I said, of volume over time. Now, do you remember when, let's see, yeah, it was my first video, and I said, if the changes are small, the derivative in the deltas will be approximately equal. That gives you a way to understand what a derivative is. So if I calculate dv over dt, the derivative of volume with respect to time, and I get 3.9, then you could say, oh, well, that's what that means is that if I measured a change in time and measured the resulting change in volume, 3.9 is about what I get. And I did that, and I showed you that that is in fact what happened. So that gives you a way to think about what a derivative means. I don't want you to just go through the motions and do the math and get a number. The further you go in math, the more you're going to have to understand what the number means. Okay, so hopefully I've given you enough information that you can understand what a derivative means. I've made my tables, I've calculated a time and a change in volume and divided them and so on and told you it was cubic inches per second, right? I made my analogy. Hopefully that's all you need.